www.nanohub.org. You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay. So this is lecture 21, and we'll talk about PN junction diode and its IV characteristics. If you remember from the last lecture, we talked about the potential, solve the Poisson equation in the presence equilibrium where there was no current to begin with. So there was no approximation, but also in the presence of a bias, forward and reverse bias. And in that case, of course, there was a current, but I assume that there is no current. I solved the Poisson equation in isolation, and I told you the rules. Now, what will happen? Of course, the most interesting thing is IV characteristics. So let's get started. So first, I'd like to derive the forward bias formula. Then we'll talk about the nonlinear regime, and then ambipolar regime, and finally conclude. Now, these terms may not mean much to you right now, but hopefully by the end of the lecture, you will see what they mean. So we'll be talking about DC characteristics of a diode today. And the reason I mentioned this before also, the reason I put it in this format, in this matrix, is because I want you to realize that the techniques I'll be using to solve the DC of a diode, DC characteristics of a diode, exactly the same essentially for Schottky barrier, for BJTs, the MOSFET, the tricks are the same. So if you understand why am I doing a certain class of things, you will see the whole process repeated over and over again. So it will be very easy for you if you understand the basics. So again, today I'm going to focus on this part of solving equations, assuming the Poisson equation I have already solved by drawing the band diagram. I have mentioned in the last class that in equilibrium, you draw the Fermi level by following the rules, flat quasi-Fermi level, and associated continuity of the vacuum levels, and then you go back and do this. This is a simplified case where both sides of the junction is the same material, homojunctions, and therefore I have this simple rule. When I apply a bias on this device, the first rule is that, of course, I ground it on the right-hand side, let's say. That's an assumption. And then apply a corresponding bias, negative or positive, depending on the configuration on the other side, the end side. And then the barrier height gets reduced by the applied bias. That was the forward bias case. We know how to draw this. I'm just putting it here for reference. And you also know that how to calculate the width of the depletion region by replacing QVBI minus V with QVBI minus V, and correspondingly calculate the depletion width for the forward and for the reverse bias. Now, these are all from last class, so therefore, you should be able to understand this easily. But let me go on to the main topic of interest in today's lecture. So this is what I wanted to first mention physically, that what happens during forward bias, let's say. You see, in equilibrium, there is lots of electrons on the N side and very few electrons on the P side. In equilibrium, that is Ni squared divided by Na. So there is a huge density gradient. I mean, you cannot believe the amount of density gradient. 10 to the power 18 on one side. It's a humongous number. And 100 electrons trying to move around on the other side. Right? Huge density gradient. And the electrons, if it had any chance, it will immediately spread out. But as it begins to spread out, as you realize that it depletes the region, and as a result, an electric field comes up, and the electric field pushes that huge amount of electron from diffusing into it. And that's what the equilibrium situation looks like, a very intricate and detailed balance between diffusion and drift. That keeps the current to zero. Current is zero but the component that is forcing the current are humongous, probably on the order of, let's say, even if the net is 0, but individual components are significant. So as soon as you disturb the balance by applying a bias, then what happens? The diffusion remains the same. Do you realize why? Because one side is ND doped, right? Same 10 to the power 18. The other side is Na doped, acceptor doped, same 100. That I have not changed. So the diffusion force will remain exactly the same. But the drift component of it, previously I had QVBI dropped across the junction. Now I have a reduced bias dropped across the junction also. So it's a much smaller field, and immediately current begins to flow, as has been shown on the right side. You can see now the green circles are gradually moving to the right. Now, do you realize one thing, that the current flow, J sub n, electron current flow, should be going the other direction? Because anytime electron flows from left to right, the current flow associated with the electrons must be going from right to left. Similarly, for the holes, the barrier has been reduced for the holes as well. And therefore, the red circles, which are supposed to be the holes, now can flow in to the other side. And as a result, there will be a hole current. But holes are positively charged. Therefore, the hole current also goes the same way, same direction from right to left. Now, therefore, you realize there is a very interesting thing here. Just by looking at the direction of the current in your ammeter, you cannot say whether it's electron or hole, because both goes in the same direction. How would you know if something is electrons or holes in a semiconductor? What experiment? Hall experiment. Precisely right. That's why we had to do Hall experiment, because Hall gave me a correct sign to tell me whether it's a p-doped material or an n-doped material. From here, in a two-terminal device, you can never say which side is what, whether it's electron doped or it's a hole doped transport material. So let me get started on the diffusion limited regime. The diffusion limited regime for the diode will be one piece on the forward bias side. On the green region, you can see I have marked it 1. But I have also marked a piece of it in the reverse bias side, in the ash colored region, with a flat dotted line. So both actually, this one on the forward side and one in the reverse side, they actually belong to the same curve. And in an undergraduate class, you just focus on one and then you go home. And in that region, the key characteristics is that the current increases exponentially with voltage, and the proportionality factor is Q over KT. Q over KT is the proportionality factor. KT over Q in room temperature is 1 over 40, right? So therefore, you have that corresponding scale factor. Okay. So where does this exponential thing comes in? Let's try to solve this problem, and we should be able to do that. You can see I have drawn a forward biased junction characteristics. QVBI has been replaced by QVBI minus V. Do you see that I have applied a minus V voltage over there? Now, how will I calculate current in such a structure? So this is how it works. This is very beautiful actually, that people can solve such a complicated problem. You see, if I don't assume any recombination, assume no recombination, then any electron that comes in from the left side must get out from the right side. And in steady state, now steady state I'm talking about, current must be continuous, right? If you have 10 to the power 18 number of electrons, the current must go very slow. If you, on the other hand, on the right side, you have 100 electrons, current must go very fast. But current must be continuous, right? And in that case, if the current is continuous, it really doesn't matter where I calculate the current. In fact, I can calculate the current wherever I wish. And as a result, I will solve it somewhere when it be the simplest. And it's simplest when it's a minority carrier, because there's just a few electrons to think about. I could have solved it on the left-hand side also, in the drift region, but that would have been more complicated. But the continuity allows me to calculate anywhere, and then translate that current to anywhere else. So let's solve it. We already know this solution, right? We have already done this in a example problem in the class. Have we not? Steady state. Which term do I get rid of? Right there. No generation, no recombination, no photon coming in. I said no traps. So therefore, Rn and Gn, G sub n, those go also. Now, do you remember in the minority carrier, when you have a minority carrier, in that case, the electric field is approximately equal to 0. I gave a detailed explanation, right? Why the electric field is 0? It is not 0. It is approximately equal to 0, on the order of a microvolt or so per centimeter. And so I dropped that first term also. And I have dn dx. Now, this should be now very simple for you. So my solution of that region shown here in the sort of the mete color, that will be equal to the second derivative of n multiplied by dn equals 0. Now this even I can solve. This is very easy. Now before you take that second derivative and set it to 0, which is very easy, you have to understand about boundary conditions, which is not as easy to understand. It is easy once I explain it. Assume that I want to know about this region in the minority carrier side, where I have shown here in the red triangle the profile of the solution of the second derivative of the equation. What I want to know is the boundary condition that I have to put on the left side and on the right hand side. What would be the boundary condition on the left side? Well, first of all, in general, you know that n of x, I have already explained to you that how is it related to ni of equilibrium, right? And since it applies to any x, it must apply to x equals 0 plus, which is just to the right of the red triangle on the bottom figure. Now this you have also seen. The product of n and p is equal to ni squared and the difference of the quasi-Fermi levels Fn and Fp. Now do you realize that what this trick of keeping the Fermi level, quasi-Fermi level flat to the other side of the junction helps me with? Because now if you look at this yellow region, the line going vertically across the yellow region, what is the difference of the quasi-Fermi level? This must be equal to the applied voltage, because I have kept the red line flat, I have kept the blue line flat to the other side of the junction. And since there is no drop, whatever voltage I have applied, that voltage, that difference has stayed flat all the way to the line associated with that yellow circle. As a result, I can immediately put the difference of the quasi-Fermi level equal to QVBA. Beta is 1 over kT. So I just remind you this. Okay, now if this is the case of equilibrium, of course, you see when VA is 0, NP is Ni squared. Equilibrium is equal to Ni squared. That's fine. Now, at the yellow point, I know it's a majority carriers are the holes. How many holes do I have? Is equal to Na. Because do you see that the blue line and the green region for the holes, the difference has remained flat throughout this region. So at the yellow point, how many holes do I have? It must be equal to the number of acceptors. So I have that. But that immediately tells me how many minority carriers I have at 0 plus. That in equilibrium, I simply have Ni squared over Na. But as soon as I apply a bias, then it increases exponentially, right? It started, let's say, with 100, immediately becomes 1,000, 10 to the power 4, 10 to the power 5, as I keep applying the bias. Very quickly it goes up. So that will be my boundary condition on the left side. Do you realize this? I'm looking at delta n is the amount that I have above the equilibrium value, and so therefore I have a -1, which is simply whatever I have in the presence of a bias minus whatever I had in equilibrium. So that's what I have, the extra value that I have. Okay, this is one side. What's about the other side? The other side you already know. This other side is has been terminated with a metal with infinite surface recombination velocity. Excess carrier is 0. And as a result, if the excess carrier is 0, delta n will be equal to 0. W sub p is the bulk region, width of the bulk region for the p side. It may be several microns, let's say. This is not depletion, right? We are thinking about the bulk region. I have the boundary conditions, so I don't need to do anything more, right? The solution of that equation is c plus dx. At x equals wp, I know what the delta n is. That's equal to 0. Therefore, c must be equal to minus d multiplied by wp. Do you realize this? This one. And as x equals 0, I also know what the value is. So that gives me the value of c. And as a result, I'm done. That's my carrier concentration as a function of position. Does it make sense to you? Do you see? At x equals wp, if you put it in, what is the value of delta n? 0, which is what I know I should be. If VA is 0, applied bias is 0, then what should be the value of delta n? 0 again, right? Do you see that? Q VBA multiplied by beta, put VA is 0, that gives me 1 minus 1, that's 0 again. So this looks about right. This is excess carrier, right? Not the original amount. Original amount is Ni squared divided by Na. Okay, so I have the carrier concentration, but I don't care about carrier concentration. What I really need is the amount of current. That's what I'm after. So you can do the current. The current is simply diffusion term for the minority, no drift. And so therefore, you take a derivative. You can take a derivative 1 minus x divided by Wp, and that gives you a minus sign, right? Minus Wp, and you see that's the current. Do you agree with this current? Why is there a minus sign? Because it's diffusing to the right? More on the left, less on the right. Electrons diffusing to the right. Which way electron current is going to go? The opposite direction. That's why you have a minus sign. And if, of course, if it's easy to diffuse, current is high. If the depletion region is very large, then the gradient is small. So therefore, your current will be smaller. And as a result, you can get the current for the electrons. Now, can you get the current for the holes? Well, why not? The current for the holes, current for the holes is again, same procedure because barriers for the holes have also reduced. The same time barriers for the electrons have reduced. As a result, the blue triangle simply says the amount of extra holes you have. Again, a diffusion, you do the same process and you get the hole current. Again, do you see there is a negative sign? The negative sign is because holes go the same direction as the current does. So both electron and hole current, when I add them up, they will amplify each other. And that makes sense, the total amount of current. Now, I want to calculate the total amount of current, and this is the trick. I have calculated the current for the electrons on the plus side of the junction, to the right. I have calculated the current as a minority carrier for the holes on the left side of the junction. Can I simply add these two to get the total current? Of course not, because current must be added at a given point. If you are looking at the traffic flow between Chicago and Lafayette, one person cannot sit on the Lafayette side and look at the northbound lane, and another person cannot sit in Chicago and look at the southbound lane and then simply add them together, right? That will not be appropriate. Only time you can do so is if there is no car transfer going on between the north side and the south side, only then. And that was, remember, my assumption, because the whole current, although I calculated it to the left of the junction, however, in the absence of any recombination, that current must be continuous to the majority carrier to the right side of the junction. Now, at a given point, I can add, only in the absence of a recombination. So I add it, and I get the total current. You can see how it depends on NA and ND, right? And from that, I can easily show you that in the forward bias case, in strong forward bias case, this would be the formula. Do you agree? The first term within the bracket on the right-hand side that depends on the diffusion coefficient and d sub p, also sorts of things in the bracket, that's a constant. I know the doping, if I know the band gap, so I know Ni squared, silicon, remember? So silicon, so I know the whole thing is a constant. As soon as I make a device, those are given. Now, if I apply a little bit higher, few voltage higher than a few kT, then Q exponential of QVA multiplied by beta, that will be much larger than 1. So I can drop that -1. And if I drop that and take log on both sides, do you agree with me that you essentially will get a curve that increases exponentially with voltage? That's good. Forward side, that increases exponentially with voltage. What about the reverse side though? The reverse side will essentially be just a constant. Why? Because you see, as soon as you put VA as a negative number, then it's going to go to 0. And then you have a minus sign. And as soon as you have a minus sign, then as a result, the current will become a constant independent of bias. Now, where is this current coming from? This current, there's no generation and recombination, remember. So therefore, there's no current like that. What's going to happen, and I'll just give you a hint here, maybe you will try to understand yourself. What's going to happen, the ray triangle that you see, the ray triangle on the right hand side, the concentration is Ni squared divided by Na. That's the equilibrium value. And on the left hand side, you have the exponentially large value. When you have it in a reverse bias, the left side of that ray triangle will go to 0. And there will be a diffusion current going not from left to right, but from right to left, because one side is Ni squared divided by Na and the other side is 0. So this diffusion flux will go in the opposite direction. And do you see, therefore, you have a plus sign there, because when you get rid of QVBA, then the -1 there and a minus Q there gives you a plus sign. So current will start flowing in the opposite direction. No regeneration recombination. It's just the diffusion in the bulk direction. So we'll talk about now about this solution of the IV characteristics of a PN junction diode in the nonlinear regime. Nonlinear in the exponential sense, as I'll explain in the next slide. One thing we have discussed so far is the forward junction, forward bias PN junction diode, and we have seen that the current in region 1, marked by region 1, it increases exponentially with voltage, and that's because as you applied a forward bias, then the barrier, effective barrier is reduced. The diffusion current wins over the back forcing drift current, and as a result, I have an exponentially increasing carrier concentration near the junction, and that forces an exponentially increasing current in region 1, and that is shown in the blue dotted line, that the slope of that is Q over KT. Now, if we continued applying larger and larger bias, you obviously realize that the current cannot go on increasing exponentially forever. And what happens that is you pump more current through this diode, that the maximum current you can put is almost equal, maximum voltage you can put is almost like a band gap of the device. You cannot put any more. But even at that point, the current begins to get nonlinear with respect to the voltage. That's region 2 and 3. I will get started with region 3. In region 3, what you will see that one of the approximations we made of assuming that the quasi-Fermi level is flat starting from the contact to the other side of the junction, that is no longer correct. And that approximation will now break down, and this delta F sub n and delta F sub p is how much it deviates from It's the ideal characteristics at a low current case. So that's where we'll get started. By the way, this is an exact formula. The other one was a case approximation where this delta Fn and delta Fp was very small and negligible, and therefore we didn't have to write it. At the end of the day, what we'll see that this applied voltage will be reduced, effectively reduced by the current that is flowing in the device itself. So you can see now it's a nonlinear function of the current itself, no longer as simple, right? Because Jt is the total current, is the sum of electron current and the hole current. And you can see on the right-hand side on the top of the exponential also the electron and hole current sitting. So it's a nonlinear dependence, and that nonlinear dependence is reflected in region 3. So let me explain the physics. Things will become clear at that point. Now, this question about whether a quasi-Fermi level is really flat up to the junction, an undergraduate student wouldn't really ask this question because you're not expected to get into this part. But for all modern junctions, high injection, that is what it's called, when you have a lot of current flowing, is an integral part of the device operation, and a student must know about it ahead of time. Now, we have already said that a current, let's think about electron current for the time being, has a drift and a diffusion component, and this we can rewrite this in a slightly different form, something that you have already seen before. We can say that the carrier concentration N at any point in non-equilibrium condition is given by this exponential of the quasi-Fermi level minus EI. How far away is it from the quasi-Fermi level? In equilibrium, the Fn would have been E sub F. That's something we know. The beta is 1 over kT. Just remember that. So if I wanted to write the diffusion component of the current, and with that expression of N, then I can immediately take a derivative of dN dx, and you realize that there can be, in principle, in general, a gradient of the quasi-Fermi level taken out from the exponential, and the gradient of the intrinsic energy, the intrinsic level, EI, because both are sitting on the top of the exponential, so I can have a gradient there as well. And that gradient of the EI is written as the electric field E in magenta. So the second term on the numerator or on the exponential becomes an electric field, and the whole exponential term shown here in red comes out as is. You know, this is an exponential function. Now, one approximation or one assumption I have already made. Do you see what I have done here? I have assumed that both sides of the PN junction are at the same temperature, right? If the temperature is varying from point to point, right, in addition of quasi-Fermi level and EI, then of course I would have taken out another derivative with respect to temperature. But for the time being, we'll assume temperature on both sides are the same. Now, if I have that, you can see that the quantity in the bracket in the red is again Ni one more time, right? So therefore, I should be able to write that quantity in the bracket as N. So if I insert that diffusion term back in the original equation, by assuming, of course, we know that the Einstein relationship d over mu is kt over q, a single line of algebra, then you realize that the electric field term in magenta in the diffusion term comes as with a negative sign, and the first drift term in the first equation comes with a positive sign for the electric field. And as a result, when I sum them, the current will only have dependence on the quasi-Fermi level. So the gradient of the quasi-Fermi level is proportional to the current. Now this you know, already you know that. But you can immediately see, therefore my assumption of having a flat quasi-Fermi level implies that I do not have any current, right? But of course I have a current. That is the whole part of the whole derivation I did in the other day with this red arrows. So I do have current, but the point was that the current was small. So when I have a large N in the majority carrier side, I'm not talking about the right-hand side arrow now. I'm talking about the arrow on the left-hand side in the N region. In the N region, I have a huge number of electrons, right? So therefore, the gradient of the quasi-Fermi level that I need in order to drive a certain amount of current is minuscule. As a result, you can see that N is equal to ND. Take a look at that expression. If N is equal to ND, Jn, it's a constant, right? Because its current is flowing without any recombination from one side to another. Cross multiply with dx and divide by nd and mu n. The whole thing is a constant. Integrate from the left side of the contact up to the junction. That's Wn, and that gives me that the change in the quasi-Fermi level, the drop in the quasi-Fermi level, is proportional to the current. And what is that factor, by the way? Wn nd divided by, mu n nd divided by Wn, what is that? That's actually conductivity. If you go back and see that that's actually conductivity. So therefore, this quasi-Fermi level drop is essentially proportional to the amount of resistance that you have multiplied by the current. Amount of resistance you have in the bulk of the material multiplied by the current. That sort of makes sense, right? Because as the current is flowing in the majority carrier side, there will be this resistive drop or the series resistance before it comes to the junction. And that is reflected in this delta Fn. Okay, so let me pictorially show you what delta Fn really implies and what it means. So as I mentioned, this is the part of the left-hand arrow that I have focused on in getting the delta Fn and making sure that I understand how the red dotted line falls off from the left contact towards the junction side. That's how much drop you will have. Okay, so now let's take a look a little bit carefully. First, let's look at the diagram below. This is a high injection case, lot of current flowing in. You can see from the black dotted line that the quasi-Fermi level on the two contacts have been pushed up by the applied voltage VA. That's fine, no problem. But you also realize that by the time the quasi-Fermi level have come to the junction, then it has dropped by delta Fn from the N side because of this resistive drop, and correspondingly delta Fp as holes are also flowing through the majority carrier side towards the junction. And so in the junction itself, the applied splitting of the quasi-Fermi level is no longer VA. VA, it was equal to the applied voltage when they are both parallel to each other, right? Without any drop. Now, if you have a little bit drop on both sides, then the absolute splitting in the junction region will be how much? It will be VA, of course, multiply minus delta Fn and minus delta Fp. Because this is the drop, because of the series resistance, the junction does not see, right? As a result, my original equation for the minority carriers on the right-hand side of the junction, which I used to previously write at Ni squared divided by Na and the exponential of the difference of the quasi-Fermi level, red and blue you can see on the top equation, that one I cannot simply assign it equal to VA anymore, applied voltage anymore, but rather I must put the real difference at the junction. And that's why I have taken out this delta Fn and delta Fp in the exponential. Now, do you realize that delta Fn has a magnitude or dimension of energy, quasi-Fermi level. And so therefore, I don't multiply with Q. The VA, of course, is a voltage. I have to multiply with Q in order to get the dimension of an energy. And beta is 1 over kT once again. So from here, you can immediately see that if you wanted the excess carrier, not the total one, the excess carrier, the equilibrium density is how much? Ni squared divided by Na, right? Minority carrier equilibrium. So I have subtracted a minus 1 to tell you how much excess I have. Okay, now I am done. Because now I can quickly calculate the current. Again, you follow the same rule. you have that relationship boundary condition, you solve for the diffusion equation without recombination, that gives you a straight line, you take a derivative of that straight line, and that gives you the current. So you see everything is the same, except I have delta Fn and delta Fp. Now this is very important. If you realize, I just explained the delta Fn and delta Fp, both are proportional to the current, right? Now if you're trying to pump more and more current, what's going to happen? As you pump more and more current, you're applying a more bias, let's say, applied voltage. Let's say you apply 2 volts and your band gap is 1 eV. What's going to happen? Is my barrier completely disappear and it will go on the other side because the Fermi level separation is now 2 eV? Impossible. That cannot happen. What's going to happen that as you pump more current, there will be more delta Fn will rise proportionally because it's proportional to the current. And it will always keep making this thing smaller and smaller, smaller than the band gap eventually. And as a result, their junction, no matter what you do, will not ever disappear. And one thing, of course, and therefore, and this I will come back in the next problem as well, but this is why the current starts deviating from a pure exponential rise with respect to voltage. So that's something we should know. Now, one approximation, of course, which is a little difficult now, is because the quasi-Fermi level is dropping, the electric field is no longer zero, as it was the case for the minority carrier, right? In the minority carrier case, we assumed that the majority carrier is holding the potential fixed, and the minority carrier was sort of diffusing through that potential barrier. No longer, because you can see that there will be electric field and potential drop even in the majority carrier side. So this approximation, well, it's good, but not great, but in this case, you need a numerical simulation that you have been doing. No longer is possible to do analytical work any further. But you can get the physical feel that what happens at high bias, why it's nonlinear. But the exact value, well, at this point, numerical simulation is better. Now, what happens if you have a slightly more complicated situation? Now, this is called an ambipolar regime. Here, the carrier concentrations are so high that the minority carrier assumption is completely gone. It's no longer true. So I want to case that very extreme case, and we'll talk about ambipolar transport. Why ambipolar? The word means 2 polars, right? So here, previously there was minority carrier and majority carrier. When there is no minority and majority, both are playing a role, then it will be called an ambipolar transport regime. Again, only numerical solutions are truly effective, but we can also make some progress based on analytical expressions. The main point I want to make in this expression, I'll be talking about region 2, but many times region 2 and region 3 may be interchanged, depends on the diode you have. The main thing that I want you to notice, of course, we have the delta Fn and delta Fp that we just derived, but there is a 2 sitting there. And the whole purpose of this derivation to explain beta over 2. Now, in previous expressions, I just had beta, 1 over kT, but now I have that factor of 2 sitting there, and I want to explain that why that factor of 2 comes in, and why in the ambipolar regime, the slope in the exponential side becomes half of the diffusion limited regime. That's what I want to explain. Now remember, this is how I'm deriving it. When you become a big name engineer, then of course nobody will tell you what is region 1 and region 2. A technician will make a measurement, or maybe your graduate student will make a measurement, and they will bring a piece of paper that I don't understand what to do with this device, it's not behaving correctly. What you immediately do, what professors do, what managers do, is that immediately they know the physics in their head, so they immediately try to identify the slope of this region. And by looking at how it's breaking, at what point it's breaking from one slope to another, they immediately realize that what's going on in this device. Maybe the region has not been doped properly. Therefore, the region 2 has start appearing much before than it should ideally. And then they will tell the technician that, go, you must not have doped it properly. And he'll be surprised. But the reason is, of course, behind it is he or she is thinking about all the physics that defines these various pieces. So this is very important to go from the other side. We are doing analysis, but how to analyze the problem from a given data is very important. So this is the physics. We all know that n multiplied by p is ni squared in equilibrium, and if they are not in equilibrium, fn minus fp in non-equilibrium case, right? Now, and we have already seen that fn minus fp is delta VA, QVA. I have made a mistake here. You can see the Q should be inside the bracket. On the right-hand side, multiplying the exponential. But in this case, you get the idea. There is applied voltage, and you take out the quasi-Fermi level drop because it's drooping on either side, and you take them out. So the right-hand side is something you have seen already. But look at the left-hand side. Left-hand side is a little troubling because n is fine. N is ni squared divided by na because it's a minority carrier, right? In equilibrium, ni squared divided by na. And the little excess carriers that you have is delta n. Now, in general, the delta n used to be much larger than ni squared. That's why you had the triangular profile, much higher than the background carrier concentration. No problem. Think about the right-hand side factor. Na plus delta p. Now, delta p used to be so small, right? It's a majority and minority carrier. Delta p used to be so small that we used to drop delta p. And therefore, we used to write delta n is equal to ni squared divided by na and the whole thing. That's what you used to write. But if you have biased the junction so much that you are pumping a huge amount of electrons over the barrier, and in order to compensate that huge amount of minority carrier influx, a huge amount of majority carrier is also flowing in the device, right? In that case, what will happen, and that's the plot that is shown here on the right-hand side, you can see that n sub n is equal to nd, and n sub p is equal to na, and the carrier have been injected at such a high level that both of them are now majority carriers, in fact, higher than the doping density. In that case, which term should I drop? This time, I have to drop both ni squared over na, which is negligible anyway, I'd been dropping all along, but this time I'll also have to drop na, because the carriers that have come in is actually larger than the doping density. So if I take it out, do you see what's going to happen? Because NP is approximately equal to Na in this high injection regime, and therefore I will have to, if I just wanted to know what they are individually, then I will set them equal to each other, and they will individually be equal to the square root of the whole thing. Now, in the exponential part, the applied voltage is huge. First exponential term is large. -1 drops out. If I take out the -1, do you see where the 2 is coming from? The 2 is essentially just the square root of the exponential sitting inside. Now that's very important because this factor of 2 is saying the physics of the diode has fundamentally changed. Because previously it was minority carrier transport, a little bit of diffusion going on, nothing funny. But in this case, as soon as you see a factor of 2 appearing, you realize that you have flooded the PN junction with carriers, so there is no majority carrier per se. Both have become comparable, and as a result, there is a change in the slope. So in a log-log plot, you would expect the slope to be half, right? Half as before. Once again, once you know the delta n at x equals 0, then you can calculate the corresponding electron current and the hole current from this expression. Only thing is, again, I have just assumed diffusion. Obviously, you can see with this amount of delta Fn in the majority and the minority carrier side, obviously, it is not equal to just the diffusion current. Look at the right-hand side. I mean, the band EC and EV are drooping significantly, significant electric field. And so my neglect of electric field, well, that helps me to explain some of these things, but not really 100% correct. Okay. But the point I want to make, and this is something people often don't understand 100%, that no matter how much bias you apply across a junction, the junction itself, the potential barrier in the junction, is never going to disappear. There is always going to be a barrier. Yes, with large current, there will be a lot of drop in the majority carrier side, but no matter what you do, unless you burn the diode up, the junction remains. Okay, so we are proceeding through with various nonlinear part. Now let me talk about something that earned a young scientist, or not, by the time he won the Nobel Prize, he was no longer young, but he is a Japanese person, ECE606, and I want to explain that how he not only addressed the p-n junction problem, a very important issue, but he finally made quantum mechanics relevant for solid-state devices. Because before 1960s, the solid-state devices, whether quantum mechanics actually applies or not, there is a lot of doubt. And this finally ended it all. So very important and interesting aspect of the IV characteristics. So let's talk about it. This is called an ECE606 diode, and I'm looking at region 7 of the IV characteristics. And this region 7 has a little bit different characteristics than 1, 2, and 3 I talked to you about. First of all, it's occurs at a very low current regime. So that's first. So there's no business of majority, minority, and ambipolar, nothing like that. Second, this only occurs, but that they didn't know in the beginning, it only occurs if both sides are heavily doped. Do you see that in this device, in the N side of the diode, the Fermi level is actually above the conduction band. So it is degenerate on the Fermi level side. And do you also see the F sub P in equilibrium? Of course, everything is flat, so both sides are actually EF. But this is below the valence band. That means it's again on degenerate on the right-hand side. Now, the question is that how would current flow in such a structure? Now, first of all, the types of problems we had been looking into is where when you apply a bias, the minority carriers go over the hill on the other side and diffuse out, right? That's what you have been seeing. But now you will see a new current component will come through. So first of all, that if you just plot it linearly, the top plot was logarithmic and in the green region, and if I plot it linearly, then the current will have this exponential rise. I'm just replotting it, just in order to emphasize the low current part of it. Now, when you bias it a little bit, then that device, instead of following the standard dotted line on the right-hand side picture, it will now follow a strange blue curve. Current, of course, in the beginning will start with 0. In equilibrium, you cannot have any current. But apply a little bit of bias, then this strange thing happens. Do you see what's happening here? As you have applied a little bit of forward bias, the electron Fermi level has moved up a little with respect to the grounded side on the right-hand side. When the electron moves up a little, then the electrons above the Fermi level, above the conduction band on the left-hand side, will now find empty space. I'm sorry. So it will find empty space on the right-hand side. Why empty? Because it's full of holes, right? Remember, anything above the conduction band, above the Fermi level, are full of holes. Holes is absence of electrons. So electron from the left-hand side will now be able to come through and contribute to the current. Now, this current component didn't exist before, and it doesn't happen when their doping is not strong. This current, if you forward bias it a little bit more, you can see that this will try to come to this junction region, And as a result, there is no state there. And so electrons will not be able to come from the left side to the junction, to the current. And as a result, the current will drop. As a result, the current will drop. And therefore, there is this nonlinear characteristics. So this was for the first time, actually, it was shown that band gap really exists, because, previously we had optical experiments showing that electron jumps from one side to another. Nothing very precise. But this is for the first time, just by doping on the two sides, you can control the current through tunneling. And this was very unique. And as a result, this had he was honored later on with a Nobel Prize for just this effect. It turns out noise, there's another giant in the semiconductor field. Recently, there was a paper that about several years before Isaki found it out, about 2 years ago, he in fact sketched it out in his notebook. But only difference is Isaki actually experimentally demonstrated the effect, noise didn't. But he understood that if the p-n junction theory is correct, that under heavy doping conditions, this must apply. Right? So I will post an updated slide on this one. Oh, maybe I didn't delete the slide. Okay, so this was the physics I'm trying to talk about, where because of the current flow at a higher bias, essentially the tunneling is suppressed. And as a result, you can see the magenta point, the current essentially goes down. Eventually, it joins the original current. Why? Because the final current is over the barrier. That diffusion current always stays. It is this extra component that was unusual. Now, there is another aspect of the tunneling that is also important. Now, however, in the reverse bias side. You see, I'm going in the other side. Why I have said a plus VA? Because in a PN junction, my right side is grounded. That's what I have assumed. And so when I apply a positive bias, then my quasi-Fermi level always goes down. Electrons like to stay in the positive potential. And so you can see the Fn that has essentially been suppressed down as if proportional to VA. Now again, there's another tunneling, but this time is not as mysterious. Because you can see for the yellow, if the Fermi level on the right-hand side is at Fp, below the Fermi level, it's full of electrons, isn't it? Right? Quasi-Fermi level, so it's full of electrons below the Fermi level. And above that, lots of holes. However, now with the reverse bias, you can see for the yellow region that electrons will essentially tunnel from the right-hand side to the left-hand side. Okay. Now, if you apply a little bit more bias, then the current will actually increase. And as you can see in the blue region, the blue dot, the current will increase exponentially. Now, do you realize that you have actually solved this problem before? You might not have realized, but you have already solved this problem before. You remember that when we were doing chapter 1 or chapter 2 in quantum mechanics, I told you about a rectangular barrier and how to calculate current through a rectangular barrier. Do you remember that? That exercise was in preparation for this problem. Because, you see, for an electron to go from the valence band to the conduction band, it essentially has that triangular barrier that it has to cross. It could directly jump up and then go, or it could tunnel through the barrier. Now, if you apply a higher bias, then what's going to happen? The electric field will increase, right? The electric field in the junction region will increase. And as a result, if the electric field increases, that means the gradient of the potential will increase. That makes the triangular region a little thinner. And as a result, more current flows through the structure. So in fact, only modification you have to do is that in that example, you assume free electron mass. In here, you will have to assume the effective mass, because electrons are tunneling and the electrons on both sides are not free. These are effective masses for the valence band on one side, effective mass for the conduction band on the other side. Other than that, you have already solved this problem before. Okay, so the IV characteristics of the p-n junction has many phenomena, and we'll continue in the next lecture, but I have explained some of them: diffusion, ambipolar transport, and tunneling. Tunneling has two types. One is this Zener tunneling, which is the reverse bias side, and Esaki tunneling, which is the forward bias side. Esaki tunneling only occurs in heavy doping. Zener tunneling occurs all the time. If you apply large enough bias, it will occur. And as I said, that you have to understand the characteristics of the specific features of these IV characteristics so that you can identify them and troubleshoot your process. So people may depend on you to solve a particular problem in the process, and you'll have to, these are diagnostics that allows you to explore the physics inside of a diode. And we'll talk about a few more non-ideal effects in the next class.